So I just want to start sharing a little bit of the things I'm learning to use as building blocks in understanding machine learning. Most people in supply chain understand basic math, but when it gets to more complex topics, it can get confusing, it can look confusing. I want to take them and simplify them down. Today, I just want to talk about something called regularization. And so I'm just going to use the Jupyter notebook here, and we're going to discuss regularization. I don't want to get into too much about how this is used specifically. I'm going to keep these really short. I want to talk about the different norms that are used in regularization. When you use this is when you have to basically keep a model simple. So think of a model like a linear model, y equals mx plus b, okay? And in that, you've got m, which is kind of your weight. You're weighting how much x influences y. And you could have a number of those x's, and that can grow exponentially. And the more it is, the better machine learning, deep learning can really help you. So you can overfit models. In other words, you can draw lines from point to point and match exactly, but they're not going to be helpful in prediction. And again, there's other videos that I have that will cover this. But the more simple you can keep a model, the less it'll fit the training data that you have, but the better it will extrapolate into the future because you'll create more generalized rules rather than specific rules for your training data. One of the ways to do that is something called regularization. You basically constrain the weights. If a weight can get really big, it's going to put a lot of emphasis on a certain feature, you call it, or X. And this, when we constrain it, we basically say none of the X's can matter that much. And regularization is a mathematical way to do that. So I'm going to get into the math behind the regularization briefly and just kind of show what it is. Because when you look at it in the midst of like a ridge regression or a lasso regression, it can get kind of complex. I'm going to show really simply what it is and then build on those building blocks in the future. And so the first one that I really would like to discuss is called an L1 norm. Okay, and the L1 norm is going to be, think of it as, this is called latex. This is not really mandatory. I use it to keep track, but it's going to look like this, L raised to the 1. Some use subscripts. Most of the time you'll see it as superscript. And what an L1 is basically the sum of the absolute values. So if you take the sum of the absolute values of a vector, you've got an L1 normalization. So let's get an example in here. We're going to do import numpy as NP, and then from numpy lin alg, we're going to import the norm. And we're going to calculate this two ways. So let's create a really simple array. This would be like our x's. This would be the features that we're going to use to predict. We need to weight each of these features differently. So let's say we've got 1, a -2, and 3. Okay, so there is our array. Perfect. Now, what I'm going to do is I'm going to create a function that I'm going to call transform. And like I said, the L1 is really it's the sum of the absolute values. So keep that in mind. So my transform is going to take all of the array features and turn them into absolute values. So whenever I call the transform, I want it to basically take the absolute value of whatever I feed it. All right, and if you, just in case you're not quite familiar with this, I'm going to grab the second, this is the second part of the array with an index of 1. Index will start at 0, so this is going to be 1. So I'm grabbing a 1 here. Here's A, and I'm grabbing 0, 1, the specific feature of -2, because this is really where the number will change if we're doing it correctly. And I'm going to show that I can take the transform now, which is just this little function I just created, and I'm going to call the same thing. I'm going to call A1, and we should see 2. Great, so it made it the absolute value. And so now if I want to do, I can just do the sum of the transforms of all the x's, or x sub I, for xi and a. So for every, I just create this variable xi in the array, it'll take each scalar in this array, 1, -2, and 3. It'll plug it into xi, and then it'll do whatever I tell it to do to xi, in this case, the transform I created. So it'll iterate over the array, make them all absolute value, and then sum them up, which is, if you remember up here, the sum of the absolute values. That is our L1 regularization. And added an S there. Boom, we got 6. So we can do this in our head. 3 plus 2 plus 1 is 6. That's correct. Now, I pulled in this package here from NumPy norm. You can pull it in like this, or you can call it as MP norm. And we can basically just take the normalization of A and tell it we want the L1 version, and we get 6 as well. So it's a quick check. So if you just do this, it can be you not sure how it's done. This is all it's doing. It's taking the absolute value of each number and summing it together. What we can also do is we can write this, now that we understand it, in notation. So I'm going to kind of build it backwards. We know that we take each item of the array. So an array in LaTeX is a small bold. So for example, X would look like this. This is each individual. So X0, or the first X, or X1 would be 1, X2 would be -2, and X3 would be 3. The 1, 2, and 3 is just the index level, right? So X1 would be literally this first X, so 1. All of them together are known as the array X. Right, now it's bold. This stands for the entire array, right? Okay, so X bold is all of the individual X's. So what are we exactly doing? Well, we are going to be taking each Xi, right? So each individual X we're going to turn it into an absolute value. So let's add that. We're going to take the absolute value, and we're going to sum them all up. So we're going to take the sum from I equaling 1 all the way to however many there are, and in this case there's 3, and we are going to sum them up. And so this is, actually I threw a quote in there, this is going to be the mathematical notation for L1. This is a normalization known as an L1 normalization. Again, just the sum of the absolute values.